Sorry, there was some weird stuff happening with my computer. I don't know if it recorded the last little bit of jumbling that I just did, which is probably a good thing because it may have confused you. So let's go back to our PowerPoint. We were just talking about net filtration pressure. Net filtration pressure, in a nutshell, is the difference between your capillary hydrostatic pressure and your blood colloid osmotic pressure. It's basically going to determine the direction of movement. Is stuff coming into the capillary or leaving the capillary? So the net filtration pressure is positive at the beginning of the capillary on the arterial side, and that's where filtration is dominating. And then as that blood goes through the capillary, it becomes negative. In other words, reabsorption occurs. So let's diagram this out. I like to draw. It just makes stuff, helps make stuff make sense. Oh my gosh, it is way too late. So here we go. And I had a blue marker, but my blue marker is out of ink, so it's all red. Follow what I'm drawing here. This is our arterial. This is our capillary. This is our venial. A very, very complex capillary bed, right? But you can imagine what it actually would be set up at. So in our capillary bed, as the blood's flowing through the arterial, entering the capillary bed, we have a net filtration pressure that's positive, meaning filtration's occurring. Filtration is dominating. Filtration. Dominating on this side. As the blood moves through and all of that water and solutes are leaving, and what we have now is a bunch of plasma proteins. Now our blood colloid osmotic pressure is higher, and so now we have a negative net filtration, which is going to be reabsorption. It's going to cause reabsorption. So there's my analogy of the fight with a boyfriend. You kick all their stuff out in the beginning, right? You're fuming. You're so mad. Get out of my house. And they're like, wait, baby, come back. I love you. I didn't mean it, right? The reabsorption that happens, right? So you kick everything out and then you take some of it right back, right? Not all of it, right? Some of it's going to stay in the interstitial fluid. Some of those cells need those things that were just kicked out from the filtration. However, along with them some of those things coming back in, there's also some of the waste products and metabolic byproducts and things like that that need to get back into the blood to go to the liver or kidneys or wherever. So that's what's going to be reabsorbed. So on the arterial end, we have filtration. On the venous side, we have reabsorption. And that's all driven by our net filtration pressure, which is a balance of our capillary hydrostatic pressure and the blood colloid osmotic pressure. All right, lots of vocabulary. You have to master the vocabulary in order to understand this section. All right, when there is no net movement, just about 2/3 through that capillary. If you look back at the drawing, hopefully you copied the drawing that I just did, go about 2/3 through that capillary, and that is where there's almost a net filtration of 0. There's pretty much a net filtration of 0. This is where the capillary hydrostatic pressure and the blood colloid osmotic pressure are just about equal, and so there's no net filtration pressure at all. So reabsorption predominates on that venous side or venual side of the capillary. This is where the capillary hydrostatic pressure falls below that blood colloid osmotic pressure, so it's reversed, and it's because all of this water and solutes were already kicked out at the beginning, and now we have a very concentrated blood that is rich in protein. So water moves back into the capillary. More water leaves the bloodstream than is reabsorbed, though. So overall, there is this difference of about 3.6 liters per day that is stuck in our interstitial fluid and doesn't enter our blood, right? So think back at that picture we just drew. I had filtration at the beginning of our capillary bed, reabsorption at the end of our capillary bed. There is a difference between the amount of water that's filtered out and the amount of water that's reabsorbed. It's a difference of about 3.6 liters per day. So this is wood be left just kind of chilling and waiting in our interstitial fluid, right, building up, and that's that fluid retention or edema, right, that swelling that happens sometimes. What actually happens is our lymphatics pick that up. The lymphatics act as this extra little vacuum sucker, sucking up all the extra stuff that our blood capillaries did not reabsorb. We'll talk about that stuff in the next chapter, but that's an important part to understand. Here's the drawing. If you didn't understand what the heck I was just trying to draw, this is it. So you have your arterial side, and then you have your venous side. Filtration dominates on that arterial side. Reabsorption dominates on the venous side, and there's no net movement about 2/3 of the way through. Overall, you have more being filtered out than being reabsorbed. That extra is being picked up by the lymphatic system. Here you can also see the numbers of CHP and BCOP. You do not have to know the 35s and the 25s and the 24 liters a day and 20.4 liters per day and all of those terms that are on here. You just have to understand the idea and the concept behind it. We're thinking big picture stuff, not nitty-gritty details, because trust me, there's enough nitty-gritty details without you having to know those specific numbers. So there is variation within capillary exchange rates. Any condition that affects our blood pressure or the osmotic pressure of our blood or the concentration of our interstitial fluids can shift the hydrostatic and osmotic forces. So if your blood pressure is very high, that could cause edema, right? Let's think about this. Go back to my drawing here, my handy dandy drawing of science. You have very high blood pressure, right? So typically the flow and pressure is decreased through the capillary to allow for this filtration and reabsorption to occur. However, if your blood pressure is elevated, you're going to have high pressure. What's going to happen to this blood going through the capillary? It's going to be fast, right? It's not going to be slow. So it's going to zip through here. And if the blood's zipping through here, it's not going to have time to be filtered and reabsorbed, right? That's not going to happen. So, or it's not going to happen as efficiently, I should say. Not going to happen as efficiently. So you might get some of it filtered out, but not all of it reabsorbed. And then what do you have? Swelling, right? That's one of the first signs of high blood pressure. You have swelling in your ankles or swelling in your hands, right? That edema. And that's because of that increase in flow rate through our capillary beds, not allowing for that exchange to take place, not allowing for that reabsorption to take place because it's going too fast. So if hemorrhaging occurs, then the blood volume and blood pressure are declining because of a hemorrhaging situation. That's going to cause your colloid osmotic pressure to be reduced, and that causes an increase in capillary reabsorption, right? You have this decrease in CHP, which is going to decrease the amount of filtration that occurs, and therefore more fluid is going to be drawn into the blood to bring up your blood volume and therefore bring up your blood pressure, kind of as a backup plan, kind of all hands on deck. We're hemorrhaging. We need as much blood volume as we can get type of a thing. It's called the recall of fluids. There's other variations, like when you're dehydrated. When you're dehydrated, the blood plasma volume and pressure are going to decline. That's going to cause a capillary hydrostatic pressure to be reduced and an increased blood colloid osmotic pressure. So if you have a high CHP, or if your CHP rises, your capillary hydrostatic pressure rises, or your blood colloid osmotic pressure decreases, your filtration is going to increase, and that's going to cause this edema, right? I think we just talked about that. So there are some review questions. You can go back and answer these questions about this little section. We're going to keep plugging along here, talking about homeostatic mechanisms for the cardiovascular regulation. So in order to ensure that there is enough blood flow through all of our tissues, or tissue perfusion as it's called, the blood flow has to match the changes in oxygen demand and nutrients within each of our body regions and each of our body organs. So for instance, when you're not eating and you're not digesting food, your arteries that are going to your digestive system aren't going to be dilated, right? They're going to be redirecting the blood maybe to your skeletal muscles or something like that, right? Or to your brain. So the blood flow is going to be readjusted depending on the demand for oxygen. That demand for oxygen is based on the metabolic activity that is put forth by those particular organs. So there's really three regulatory mechanisms, right? You have that autoregulation, at the local level, and then you have the central regulation, which can be neural or endocrine. And we talked about those earlier in another lecture. So it's super important you understand there's 3 ways that things are regulated in your body. Autoregulation at the local level, and then centrally controlled is your endocrine and nervous system. So those are typically activated once autoregulation has been tried and fails. So through autoregulation, you have this change in, there we go, change in blood flow within the capillary beds. This is kind of regulating those precapillary sphincters, shunting blood this way or that way. It's also activating vasodilators, which are little local chemicals which will allow the arterioles to dilate and redirect blood flow at the local level. Centrally, we have the cardioacceleratory center of our medulla oblongata and the vasomotor centers. These are increasing cardiac output. They're reducing blood flow to the non-essential or the inactive tissues. And then we also have vasoconstrictors that act in the endocrine system, like norepinephrine, which are going to produce a more long-term increase in blood pressure. And those effects are going to last much longer. So here is a homeostatic diagram of all of this. And the way this reads, you start with the little start arrow at the bottom. You have, homeostasis is disturbed. You have some type of physical trauma or chemical change, like a decreased oxygen demand or an increase in pH or an increase in carbon dioxide or an increase in tissue activity. You start pumping iron or whatever. So there's going to initially be inadequate local blood pressure and blood flow to that particular area. So that's going to cause a decrease in resistance and an increase in blood flow to that area, which can restore homeostasis. However, if it doesn't, if the demand is too high and your body's just not getting the oxygen or whatever that it needs, so you're going to kick in your neural and endocrine systems. You're going to activate your cardioacceleratory centers or your endocrine response to bring in more blood volume and blood pressure, and therefore bring everything back to homeostasis, right? Or it's the whole system in picture order. Your brain senses these changes by using baroreceptors. Baroreceptors are, if you remember back from last semester, they're specialized receptors that respond, they're mechanoreceptors. They respond to changes in blood pressure. They're located in the walls of the carotid sinuses, in the neck, right, carotid arteries, the aortic sinuses, which are right at the base of the aorta, right before the coronary arteries, and the right atrium. So you're getting measurements of output to the brain, output to the body, and you're also getting measurements of blood input back to the heart through baroreceptor reflexes. So if all of a sudden there's a whole lot of venous return, your heart's going to respond by pumping more blood out and increasing cardiac output, right? And vice versa. So let's take a look at, I have another graphic organizer for you, and I was just wondering a good time to draw it, and we may as well just do it now. We're going to draw a graphic organizer of the control of the cardiovascular system. So in the middle, we'll just write the word control. Scoot over. Control of CV system, right? Control of cardiovascular system. So we have autoregulation. Autoregulation. This is using vasoconstrictors and vasodilators. Vasoconstrictors are things like prostaglandins. You're going to see that word a lot. We've heard that word before. It's just a local chemical signal. It's a generic term for a cell-to-cell signal, a prostaglandin. It's a little cellular hormone that communicates with other local cells. Then you have vasodilators. These are things like nitric oxide, pH changes can be a vasodilator, potassium or hydrogen ions, inflammation can bring about vasodilation, right? So these are vasodilators that work at the local level. Then we have endocrine. Endocrine control. With endocrine control, we have things like aldosterone. That should sound familiar, right? Remember that from our chapter on hormones, aldosterone, which is regulating our sodium retention or output. Aldosterone works to increase blood pressure. I just drew an arrow up in BP, increase blood pressure. Or we have something called atrial natriuretic peptide, ANP, or BNP. These actually work to decrease blood pressure, ANP and BNP. We also have erythropoietin, or EPO. EPO works to increase red blood cells, RBC. We have angiotensin II. Angiotensin II. Angiotensin II works to increase blood pressure. And finally, ADH, antidiuretic hormone, also works to increase blood pressure. Finally, we have neural control. This is all done through the medulla oblongata. In the medulla oblongata, you have a vasomotor center and a cardiovascular center, CV, I just abbreviate. Your vasomotor center can control vasoconstriction and vasodilation. With vasoconstriction, it's going to release norepinephrine. For vasodilation, it's going to release nitric oxide by means of acetylcholine. So acetylcholine will be released, and acetylcholine will tell special cells to release nitric oxide. In our cardiovascular center, we are going to monitor baroreceptors. So it's getting feedback from those baroreceptors at the aortic bodies, at the carotid bodies, and at the right atrium. And this has the inhibitory through the parasympathetic. I'm just abbreviating because I'm running out of room. And it could also have acceleratory through the sympathetic. So sympathetic or parasympathetic pathways would be utilized depending on the input from the baroreceptors. Baroreceptors will say, oh, we need to accelerate or inhibit whatever's going on based on the input on the blood pressure. So, and that's pretty much what all of these slides are going to say. Baroreceptors, increased stimulation is going to cause a decrease in cardiac output, vasodilation, inhibition of the vasomotor center. Decreased baroreceptor is going to increase cardiac output, widespread vasoconstriction, and sympathetic activation. And that's exactly what this graphic organizer, this depiction, showing you. Pick a direction to start. You have a decrease in blood pressure, so your baroreceptors are inhibited. That's going to activate your vasomotor center, get your cardioacceleratory center stimulated, inhibit the cardioinhibitory center, increasing cardiac output, constricting your vessels, getting your blood pressure back up, and vice versa for increasing blood pressure. You can pause the video here, go back and review this little section. As we're winding down, we're going to talk about endocrine responses to changes in blood pressure and blood volume. So the endocrine system is getting both short-term and long-term regulation of our cardiovascular function, right? This is utilizing the heart, the kidneys, as well as the pituitary gland, which releases ADH. We already graphically organized all of these hormones on the graphic organizer that we just used, and I just invented a word, graphically organized. So the hormonal response to low blood pressure. In reality, in terms of like life survival, it is more important to maintain a higher blood pressure than to lower your blood pressure. So if you think about humans and how they're supposed to live and how we're supposed to, have an active lifestyle, etc., how we're supposed to eat and how we're supposed to exercise and maintain healthy body weights. Our blood pressure should never be elevated unless it's during a time of sympathetic activation, right? So when our blood pressure is decreased, this is typically during some type of traumatic event, like you cut your arm off, or tiger just bit your leg, or whatever. You're hemorrhaging, you're bleeding. There's something going on where you have a loss of blood volume and therefore a loss of blood pressure. So the body responds by having multiple plans in place to keep your blood pressure elevated. There's not that many plans in place to lower your blood pressure, and it's because innately our bodies tend to already maintain our own blood pressure at a certain level. If we're living a healthy lifestyle, we shouldn't have elevated blood pressure. So a lot of students say, well, why are all these mechanisms in place to increase our blood pressure when most people have high blood pressure? And that's why. It's because just by nature, we're not supposed to have high blood pressure, right? Our bodies are kind of made to maintain our 120/80, so to speak. So some long-term hormones: ADH, antidiuretic hormone; angiotensin II, EPO, aldosterone. We just put these on our graphic organizer. Let's look at how they work and what exactly they do. So in a given scenario where we have a decreased blood pressure, in the short term, you're going to have sympathetic activation. Oh my gosh, there's not enough blood, blah, blah, blah. Increase cardiac output, constrict the arteries, get that pressure up very, very quickly. Sometimes that's not enough. So for the long-term effect and kind of a backup plan and a supportive effort to get that blood pressure back up, renin is going to be released by the kidneys. The kidneys have a very intimate relationship with our blood, as our kidneys are filtering our blood. So as the kidneys kind of sense, there's low pressure going on here, renin will be released. When renin is released by the kidneys, it goes to the liver, where it is converted to angiotensin I. Angiotensin I, again, floats around the blood. It's a hormone, goes to the lungs. In the lungs, it is converted into angiotensin II. There is an enzyme that's only in the lung tissue called angiotensin converting enzyme, or ACE, ACE. ACE is going to convert the angiotensin I from the liver to angiotensin II. Angiotensin II is going to cause ADH and aldosterone to be released. ADH is going to retain water at the kidneys, and aldosterone is going to retain sodium at the kidneys, if you recall our endocrine system stuff from last semester. The other thing that our kidneys are going to do is release EPO, or erythropoietin. So along with decreased blood pressure and needing the aldosterone and needing the ADH, our kidneys are also going to say, well, if we're adding blood volume, then we also need to add blood cells. So let's go ahead and make erythropoiesis happen. Let's accelerate that. So EPO is released from the kidneys, accelerating the creation of red blood cells from the bone marrow. So all of that ultimately is increasing blood volume and therefore increasing blood pressure and getting us back to homeostasis. Now, as I was saying, it's not a normal natural response to have elevated blood pressure for extended periods of time. So there's really only two backup plans for this, and that is ANP and BNP. If there is high blood volume coming back to the heart, maybe during diastole, the right atrium stretches a little bit because increased venous return, ANP, or atrial natriuretic peptide, is going to be released, ANP. And this is released from the atria itself. And there's also brain natriuretic peptide, which is released from the ventricular muscle walls. So a decrease in blood volume and a decrease in blood pressure is going to decrease the stress on the heart and therefore decrease the production of those natriuretic peptides. But the increase of blood volume and pressure is going to increase the amount of those peptides. So this is how those peptides work. ANP and BNP are basically going to increase the amount of water that's being lost at the kidneys. They're doing the exact opposite that ADH and aldosterone did. So ADH and aldosterone were retaining sodium, retaining water. ANP and BNP are increasing sodium loss, increasing water loss, reducing thirst, inhibiting ADH, and aldosterone, and they're dilating the peripheral vessels to decrease the pressure. So overall decreasing blood pressure, overall decreasing blood volume, getting you back to homeostasis. You can pause the video here, go back and review. Let's keep plugging away. I know this is a long one, but I just got to get this done, guys. Sorry. We talked about baroreceptors. Let's mention chemoreceptors. Chemoreceptors work differently. So baroreceptors were specialized mechanoreceptors that were responding to changes in pressure throughout the vessels. Chemoreceptors are specialized and they're responding to changes in blood as well as cerebrospinal fluid, any change in carbon dioxide concentrations or oxygen or pH. And as we move through the next couple chapters really, you're going to see the relationship between pH and carbon dioxide. So they're pretty much the same thing. The chemoreceptors in our body are located in the carotid bodies and the aortic bodies. So in the carotid arteries and the aorta, right near those baroreceptors, right? They're also on the ventrolateral surface of the medulla oblongata. The medulla oblongata has one of the few breaks in the blood-brain barrier, and so it can kind of dipstick the blood, test it, double check for the concentrations of oxygen, carbon dioxide, as well as pH. So stimulation of these chemoreceptors is going to trigger a coordinated effort of the respiratory and cardiovascular system. Let's take a look at how it works. So if you have increased carbon dioxide levels or a decreased pH and oxygen levels in your blood and CSF, your chemoreceptor is going to be stimulated. And that's going to stimulate your cardiocirculatory centers and your vasomotor center. That's going to increase your cardiac output. It's going to cause vasoconstriction. It's also going to affect your respiratory centers that are within the medulla oblongata to get your respiratory rate up, basically saying, whoa, we have so much carbon dioxide building up, we need to get rid of it. We don't have enough oxygen, we need to bring in more, right? So your heart's going to pump faster and you're going to start breathing faster, and therefore you're going to breathe out all of that excess carbon dioxide and breathe in more oxygen to get back to homeostasis. You can pause the video here, go back and review this little section on chemoreceptors. Let's talk about the adjustments that occur in our cardiovascular system during exercise. So at rest, our cardiac output on average is 5,800 milliliters per minute. During light exercise, there's 3 basic changes that take place. And light exercise is dependent on your level of fitness. For some people, this might be walking, this might be jogging. So again, it kind of depends on where you are in the fitness spectrum, but there's 3 changes that take place. Vasodilation, vasodilation occurs, therefore peripheral resistance drops, and capillary blood flow increases, right? So you're going to get more tissue perfusion. As the venous return increases with the skeletal muscle contraction, there's also going to be increased respiration. That's going to create this negative pressure in the thoracic cavity. That's going to create this respiratory pump squeezing, helping to squeeze that blood into the vena cava and into the right atrium. The respiratory pump acts like a kind of extra skeletal muscle pump, getting that blood back into the heart. And you also have a cardiac output that can increase up to 9,500 milliliters per minute. And this is mostly due to that increased venous return. And the increased venous return is because of the respiratory pump. So as that respiratory pump is activated with increased oxygen demand, you're therefore going to increase your cardiac output just because that respiratory pump exists. Then during heavy exercise, right? So here is where our cardiac output is reaching maximum levels, more than 3 or 4 times what our resting levels are. Major changes in peripheral blood distribution. You have increased blood flow to the skeletal muscles, help get that carbon dioxide out or that lactic acid out, and help get fresh oxygen into the area so those cells can metabolize. It's also increasing the blood flow to the skin. As the blood flows closer to the surface of the skin, the body heat's allowed to escape and therefore keeping you cool. You're also going to reduce the flow to the digestive system. As you're exercising, you're not eating while you're exercising, you're not digesting while you're exercising, so your body routes all the blood that would normally be going to your digestive system and sticks it to your skeletal muscles and brain so that you can maintain your normal function. Brain flow, the flow of blood to the brain remains unchanged no matter what the situation is, unless there's some type of serious hemorrhaging somewhere. Under normal conditions, exercising or not, the flow to the brain remains the same. And here you can see that nice little graphic. The brain's always about 750 milliliters per minute. Take a look. At rest, the majority of the blood, look, you got a lot of it going to your abdomen, skeletal muscles, kidneys, right? During light exercise, look, kidneys decreases, abdomen and your abdominal viscera, your digestive organs decrease. Look at your skeletal muscles, that increases. Other tissues are decreasing, that is important. Skin increasing from 500 to 1500. Look here, now we're at heavy exercise. Our output now is much larger, right? That arrow is much bigger. We're getting less to the kidneys, right? We're getting less to the viscera, we're getting more to the skin and more to the skeletal muscles. Brain remains unchanged. So the cardiovascular performance is going to improve with training. Your body has to get used to doing that. So trained athletes tend to have bigger hearts, bigger stroke volumes. They can maintain a normal blood flow at a very low heart rate. Some athletes have, resting heart rates in the 30s, and that's because their heart is so strong that it doesn't have to pump as much or as fast to have the same cardiac output. So maximum cardiac output can be actually higher in an athlete than compared to a non-athlete. One of my friends is like an ultra marathoner, and her resting heart rate is like 37 or something. It's really awesome. Good for her. All right, you can pause the video here, go back and review these 3 questions. Let's talk. This last little section from the chapter is all about the compensation mechanisms for responding to blood loss. And obviously, your body has built-in clotting mechanisms in the form of hemostasis and that whole clot formation with the cascading pathways. But when that fails, because there's significant blood loss, the entire cardiovascular system has to adjust. So immediately, you have to maintain your blood pressure and blood flow in the periphery, especially to the brain and heart itself. So the long-term problem is then, restoring the blood volume, getting it back up. And we can lose up to 30% of our blood volume without impacting our organs in a major way. So that's a pretty good statistic there. So the aortic and the carotid reflexes are going to increase cardiac output, cause that vasoconstriction, and that's going to obviously maintain our cardiac output by increasing heart rate. So your heart rate skyrockets, but your vessels are constricted, so that's still maintaining flow everywhere. The combination of the stress and anxiety is going to increase your sympathetic output. It's going to cause that vasomotor tone to increase and constriction of the vessels on the venous side so that the blood is staying on the arterial side instead of pulling and kind of slowing down in the venous side. That sympathetic activation is going to cause the release of epinephrine and norepinephrine. It's going to cause an attempt at an increase in cardiac output and ADH and aldosterone to be released and stimulated. In terms of long-term blood loss, well, here you're going to have a decrease in capillary blood pressure, which is going to trigger that recall of fluids into from the interstitial space into the blood. So you have aldosterone, ADH promoting fluid retention, thirst increasing, additional water obtained from increased absorption from the digestive tract, and EPO stimulating the maturation of those red blood cells. Here's the homeostasis mechanism. You have extensive bleeding occurring. You have a long-term hormonal control through ADH, angiotensin, aldosterone, EPO. You have your baroreceptors and chemoreceptors that are stimulating the sympathetic nervous system and the cardiovascular center, all in the name of increasing blood volume and blood pressure. There's also shock that can occur. This is acute cardiovascular crisis can bring your blood pressure down so low and create such an inadequate peripheral blood flow. It's most common when you're hemorrhaging and if there's heart damage, like a heart attack. The normal homeostatic mechanisms can't function at this point. The circulatory shock is a special version of shock where the feedback loop is beginning while even when the blood loss is greater than 35%. So the body's just trying to compensate, but it can't because there's too much blood loss. So progressive shock is when blood volume is dropping by more than 35%. Remember, we said that your body can maintain normal functions with a loss of 30%, but when we get more than 35%, now your blood pressure is going to remain low because your body can't compensate. The venous return is reduced, your cardiac output's inadequate. That low cardiac output is going to reduce the blood flow to the heart. This could damage the myocardium, the heart muscle itself, lead to a further reduction in cardiac output. Reducing that cardiac output is also going to accelerate oxygen starvation in our peripheral tissues. So this is going to cause local changes in pH and oxygen concentrations throughout the body. That pH change can increase or decrease capillary permeability, further reducing blood volume, and it can have widespread effects throughout the body. The shock can then become irreversible. When the carotid baroreceptors trigger the vasomotor centers, sympathetic output can cause that widespread vasoconstriction, reducing the peripheral circulation, increasing blood flow temporarily to the brain. And then without treatment, that blood pressure can drop again. So the heart's seriously damaged at this point, and the cardiac output continues to decline until eventually there's circulatory collapse. This is when the arterial smooth muscles and precapillary sphincters can't contract, so you have widespread vasodilation. Basically, your body is saying, I don't know what else to do. I really need help. This is it. Immediate fatal decrease in blood pressure, cessation of blood flow. That's obviously terminal. So this is the feedback loop that we were talking about. So you have severe reduction in blood volume, decreasing cardiac output, decreasing arterial pressure, decreasing peripheral blood flow. This leads to an increase in the partial pressure of carbon dioxide and lactate and decreased pH. This can all create this positive feedback loop system, leading to damaged heart muscle tissue, where eventually, if that feedback loop continues and there's no response from the body, we get maximum vasoconstriction, irreversible cardiac muscle damage, decreasing arterial pressure, and then circulatory collapse, which leads to death. So this is the review for this section. You can stop the video here, go back and review. I believe that is it. We finally finished this wonderful chapter. It was a cool chapter, very long, lots of physiology, and please let me know what questions you have. Have an awesome day. Bye.